What if, right now, as you're listening to this, you're surrounded by an invisible language that controls every atom in your body, every star in the sky, and every thought in your mind? A language so powerful that it can predict the future, reveal hidden worlds, and even bring things into existence that were never there before. A language that might be older than the universe itself. Right now, you're probably settling into your favorite spot. Maybe you're in bed, maybe you're curled up on the couch. The day is winding down and your mind is ready to let go of all those urgent thoughts that have been competing for attention. This isn't your typical science video. It's designed to help you unwind, to let your mind drift. And yes, maybe even to fall asleep, but your brain doesn't stop working just because your body is ready for rest. While you're settling in, relaxing, letting go of the day, you'll be absorbing something remarkable. You'll experience what it feels like to truly understand a piece of our universe. So settle in, get comfortable, and let your curiosity carry you wherever tonight's journey leads. Tonight we're going to explore one of the most fundamental questions about reality itself. It's a question that has puzzled philosophers, scientists, and mathematicians for centuries. Did we invent mathematics or did we discover it? Is math something we created to make sense of the world around us, like language or music, or is it something deeper, something that was already there waiting for us to uncover it? Picture this for a moment. You're holding a calculator in your hands. It's just a simple device filled with circuits and silicon. But somehow, when you press those buttons, you're tapping into something that can predict the future, reveal hidden patterns in nature, and even tell us about places in the universe we've never seen. How is that possible? How can something made by humans reveal truths about reality that we never knew existed? The answer to this question might change how you think about everything. It might change how you see the numbers on your alarm clock, the geometry in a spider's web, or the rhythm of your own heartbeat. Because if math wasn't invented by us, if it was discovered instead, then we're living in a universe that's far stranger and more beautiful than we ever imagined. Over the next hour, we'll wander through this mystery together. We'll visit moments in history where math revealed secrets about the universe before anyone had even looked for them. We'll explore cultures that counted in ways you've never considered. We'll venture into the realm of impossible numbers that somehow make quantum physics work. And we'll ask the ultimate question: if math didn't exist, would reality still function? So let your breathing slow down. Let your muscles relax. Your conscious mind can rest while your deeper understanding awakens. We're about to embark on a journey into the heart of reality itself. Let's start with something that should be impossible. In 1846, a mathematician named Urbain Le Verrier was sitting at his desk in Paris, surrounded by papers covered in equations. He had never looked through a telescope. He had never studied the night sky. But somehow, using nothing but mathematical calculations, he was about to discover a new planet. Picture yourself in his position. You're staring at numbers on a page, equations that describe the orbit of Uranus. Something's not quite right. Uranus isn't moving exactly where Newton's laws say it should be moving. It's wobbling slightly, as if something invisible is tugging at it. Most people would assume there's an error in the calculations. But Le Verrier had a different idea. He believed that the math was right, and reality was the thing that needed explaining. So he used those equations to predict where an unknown planet would have to be located to cause Uranus to wobble in exactly the way it was wobbling. He calculated its mass, its distance from the Sun, even its orbital period. Then he wrote a letter to an astronomer in Berlin and told him exactly where to point his telescope. The astronomer found Neptune within 1 degree of Le Verrier's prediction, a planet discovered on paper before it was ever seen. Think about that for a moment. math revealed a world that was hiding in the darkness of space, 2.8 billion miles away from Earth. But that's just the beginning. Let your mind drift back to 1928, to a young physicist named Paul Dirac. He was working with the equations that describe electrons, trying to make them compatible with Einstein's theory of relativity. The math was elegant, beautiful even, but it had a problem. It predicted that for every electron there should be another particle with the same mass but opposite charge. This was mathematically necessary, but it seemed physically impossible. Nobody had ever seen such a particle. Most physicists thought Dirac had made an error, but Dirac trusted his equations. He announced that antimatter must exist even though no one had ever detected it. 4 years later, Carl Anderson discovered the positron in cosmic rays exactly as Dirac's equations had predicted. Again, math revealed something about reality that nobody knew was there. But this time, it was even stranger. The equations didn't just predict a new object in space, they predicted a new type of matter entirely, a mirror world of particles that annihilate ordinary matter on contact. How does this happen? How can symbols on a page tell us about things that exist in the deepest reaches of space or in the quantum realm? If math is just a human invention, something we created to help us count sheep or divide up food, then why does it have this uncanny ability to predict aspects of reality that we've never experienced? Consider what happens when you use a calculator. You press buttons and numbers appear on a screen, but somehow those numbers correspond to something real in the world. If you calculate the trajectory of a baseball, the ball actually follows that path. If you calculate the amount of medicine needed for a patient, that exact amount will have the predicted effect. The math doesn't just describe what happens, it predicts what will happen. This is what Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. It's unreasonable because there's no obvious reason why a system of symbols invented by humans should be able to reveal truths about the universe that we never suspected existed. Think about language for comparison. When we invented words like chair, or love, or democracy, we were creating tools to describe things we already knew about. But mathematical equations seem to work differently. They don't just describe what we know, they tell us about things we don't know yet. They point toward discoveries waiting to be made. Einstein's field equations predicted that massive objects would warp space-time before anyone had ever observed this happening. Schrödinger's equation predicted quantum tunneling before anyone had seen particles pass through barriers. Maxwell's equations predicted radio waves before anyone had transmitted a signal through the air. It's as if math has a life of its own, independent of the mathematicians who work with it, as if the equations know things about the universe that we haven't figured out yet. They sit there on the page, waiting for us to understand what they're trying to tell us. But here's where it gets really strange. These mathematical predictions don't just work sometimes, they work with extraordinary precision. When Einstein predicted that gravity would bend light, astronomers measured the exact amount of bending his equations specified. When quantum mechanics predicted the magnetic moment of an electron, experiments confirmed it to 11 decimal places. This level of precision suggests something profound about the relationship between math and reality. It suggests that math isn't just a convenient tool for describing the world. It seems to be built into the fabric of reality itself. Imagine you're an alien visiting Earth for the first time. You watch humans scribbling symbols on paper, and somehow those symbols allow them to predict eclipses, build bridges that don't fall down, and send rockets to other planets. Wouldn't you wonder if those symbols were tapping into something fundamental about the universe? Wouldn't you suspect that these humans had discovered a kind of code that was already written into reality. That's the mystery we're facing. Math works too well to be just a human invention. It reveals too much about the universe to be merely a tool we created. It's almost as if we're archaeologists and math is the ancient language we're slowly learning to read, a language that was written into the structure of reality long before humans existed. But if that's true, then what are we really discovering when we do mathematics? Are we uncovering the universe's native language? Are we reading the code that makes reality possible? Or are we discovering something even stranger, that we ourselves are mathematical beings living in a mathematical universe, trying to understand our own deepest nature? The answer will take us on a journey through the history of counting, the patterns hidden in nature, and the strange realm of impossible numbers that somehow make the quantum world work. We'll discover that this question, whether math is invented or discovered, isn't just about mathematics. It's about the nature of reality itself and our place within it. For now, let your mind rest with this thought. Every time you see a number, every time you notice a pattern, every time you use math to solve a problem, you're participating in one of the deepest mysteries of existence. You're engaging with something that might be more fundamental than matter, more basic than energy, more essential than time itself. The numbers are waiting for us to understand what they're really telling us about the universe we call home. Let's step back for a moment and consider the other side of this mystery. Maybe we're overthinking this. Maybe math is exactly what it appears to be, a tool. Something we created, like hammers or wheels or language, to help us navigate the world more effectively. Picture yourself 40,000 years ago. You're sitting around a fire with your tribe and you need to keep track of things. How many people went out hunting? How many came back? How many days until the next full moon? You don't have numbers yet, but you have fingers. You have small stones. You have notches you can carve into wood. This is how it started. Not with grand theories about the universe, but with the simple human need to keep track of things. The earliest mathematical artifacts we've found aren't elegant equations or geometric theorems. They're tally marks, scratches on bone and stone, each one representing something real and immediate. One mammoth, one day, one person. The Ishango bone, discovered in what is now the Democratic Republic of Congo, is over 20,000 years old. It's covered with small notches arranged in groups. Some archaeologists think it might be a lunar calendar. Others believe it's a record of some kind of trade. But what's clear is that someone, tens of thousands of years ago, was using physical marks to represent abstract quantities. Think about what a radical leap this was. These early humans weren't just living in the immediate present anymore. They were creating symbols that could represent things that weren't there. A notch on a bone could represent a buffalo that had already been eaten, or a day that hadn't happened yet. They were inventing the concept of number itself. But now think about this. Different cultures invented different number systems. The Babylonians used base 60. That's why we have 60 minutes in an hour and 360 degrees in a circle. The Mayans used base 20, probably because they counted on their fingers and toes. The Romans created a system based on adding and subtracting symbols. The Chinese developed a completely different approach altogether. If math were a universal language built into the fabric of reality, wouldn't every culture have discovered the same system? Wouldn't there be one obvious way to represent quantities and relationships? Instead, we find this beautiful diversity of approaches, each one reflecting the particular needs and perspectives of the people who created it. Consider the concept of zero. This seems fundamental to us now, but it took thousands of years for humans to invent it. The ancient Greeks didn't have zero, the Romans didn't have zero. For most of human history, the idea of nothing being something was so counterintuitive that it simply didn't occur to anyone. When zero finally appeared in India around the 5th century, it was revolutionary. But it was also controversial. European mathematicians resisted the concept for centuries. They found it philosophically disturbing. How could nothing be something? How could the absence of quantity be a quantity itself? This tells us something important about the nature of mathematical concepts. They're not inevitable discoveries waiting to be found. They're creative inventions that require imagination, cultural context, and often a willingness to think in ways that feel unnatural. Even our most basic mathematical operations reflect human choices. Why do we add from right to left? Why do we use the symbols we use? Why do we organize geometric shapes the way we do? These aren't universal truths, they're conventions that emerge from particular historical circumstances and cultural needs. The decimal system we use today only became dominant because it was promoted by European colonial powers. There's nothing inherently superior about base 10. It's just what happened to spread. In an alternate history where the Babylonians had conquered the world, we might all be using base 60, and it would seem just as natural to us. Language offers a perfect parallel. Every human culture has developed language, but the languages themselves are wildly different. English, Mandarin, Arabic, and Swahili all serve the same basic function of communication, but they do it in completely different ways. They have different sounds, different grammatical structures, different ways of organizing meaning. If an alien visited Earth and observed humans using language, they might wonder whether language was invented or discovered. They might notice that language allows humans to share complex ideas, coordinate behavior, and even think about abstract concepts. But they would also notice that languages are clearly human creations, shaped by history, culture, and practical needs. Math might work the same way. It's a tool that emerges naturally from human cognitive capabilities, but the specific forms it takes are cultural inventions. We needed a way to quantify, to measure, to predict, and to organize information. So we created systems of symbols and rules that could serve these purposes. This would explain why math is so useful without requiring us to believe that it has some mystical connection to the fabric of reality. Of course, math works well for describing the world. We designed it to work well for describing the world. We kept the parts that were useful and discarded the parts that weren't. Think about how mathematical concepts evolve. Calculus was invented simultaneously by Newton and Leibniz because they both needed a tool for dealing with problems involving rates of change. Complex numbers were developed because mathematicians needed a way to solve certain types of equations. Statistics emerged because people needed tools for dealing with uncertainty and large amounts of data. Each mathematical development responds to human needs and human problems. We don't discover these concepts sitting there in some platonic realm of pure mathematics. We create them because we need them. But even as we explore this perspective, something nagging remains. If math is just a human invention, why does it work so well for predicting things we've never seen? Why do our human-created symbols and rules seem to capture patterns that exist throughout the universe? Why does the same mathematics that helps us build bridges also describe the behavior of distant galaxies? Maybe the answer is simpler than we think. Maybe we're such a deeply mathematical species that we naturally create tools that reflect the mathematical structure of reality, even when we don't realize we're doing it. Maybe we're not discovering math or inventing it. Maybe we're something more like translators, converting the mathematical language of the universe into forms that our particular type of mind can understand and use. The invention argument is compelling, but it leaves us with questions that are difficult to answer. Questions that will follow us into the next part of our journey, where we'll explore the opposite possibility, that math isn't something we created at all, but something we found, something that was already there, waiting for us to notice it. Close your eyes for a moment and picture a nautilus shell. You've probably seen one before, maybe in a museum or a nature documentary. It's a beautiful spiral, elegant and perfectly proportioned. Now imagine you're examining this shell more closely, maybe running your finger along its curved surface. You notice something remarkable. The spiral follows a precise mathematical pattern. Each chamber of the shell is larger than the previous one by the same ratio, 1.618 to 1 to be exact. This is the golden ratio, a number that appears throughout nature with almost unsettling regularity. It's in the arrangement of seeds in a sunflower, the branching of rivers, the proportions of the human body, and the spiral arms of galaxies. But here's what's strange. The Nautilus doesn't know mathematics. It doesn't calculate ratios or study geometry. It simply grows, following some inner program that has been refined over millions of years of evolution. Yet somehow, its shell embodies one of the most famous mathematical constants in existence. This is the heart of the discovery argument. Math isn't something we invented, it's something we found. It was already there, written into the structure of reality itself, waiting for us to notice it. Consider the Fibonacci sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Each number is the sum of the two numbers before it. It's a simple pattern, easy to understand, but it shows up everywhere in nature. The number of petals on a flower almost always follows the Fibonacci sequence. Pine cones, pineapples, and cauliflower all display Fibonacci spirals. Even the breeding patterns of rabbits follow this sequence. Leonardo Fibonacci didn't invent this pattern in the 13th century. He discovered it. It was already there, organizing the growth of plants and animals according to rules that seem to be built into the fabric of life itself. You can find this everywhere once you start looking. Bees build hexagonal cells in their hives because hexagons are the most efficient way to divide space. Soap bubbles form spheres because spheres have the smallest surface area for a given volume. Crystals grow in precise geometric patterns that reflect the underlying mathematical relationships between atoms. None of these natural phenomena required human intervention. They were following mathematical laws long before humans existed. The math was already there, governing the behavior of matter and energy, organizing the structure of space and time. This suggests something profound about the nature of mathematics. Maybe it's not a human creation at all. Maybe it's the universe's native language, the code that makes reality possible. Maybe when we do mathematics, we're not inventing new concepts, we're learning to read the instruction manual that came with existence. Think about pi, the ratio of a circle's circumference to its diameter. We didn't invent pi, we discovered it. It was already there, hidden in the geometry of circles, waiting for us to measure it. Pi exists in any universe where circles are possible. It's not a human convention, it's a fundamental property of space itself. The same is true for e, the base of natural logarithms. This number appears in compound interest calculations, population growth models, and the decay of radioactive materials. It emerges naturally from the mathematics of exponential change. We didn't create e, we found it lurking in the structure of processes that involve continuous growth or decay. Even more remarkably, these mathematical constants are connected to each other in ways that seem almost magical. Euler's identity, e to the power of I pi plus 1 equals 0, links 5 of the most important numbers in mathematics: e, I, pi, 1, and 0. This equation is often called the most beautiful formula in mathematics, and it's beautiful precisely because it reveals hidden connections between concepts that seem completely unrelated. How could human invention create such deep, unexpected connections? How could symbols we made up reveal relationships that we never suspected existed? It's as if we're archaeologists and mathematics is the ancient city we're slowly excavating. Each new discovery reveals more of a structure that was already there, waiting for us to uncover it. But the most compelling evidence for the discovery argument comes from the universality of mathematical truths. If humans encountered alien mathematicians, we might not be able to communicate about many things. We might not share the same concepts of art, politics, or morality, but we would share the same mathematics. Pi would be the same for them as it is for us. The Pythagorean theorem would work the same way. Prime numbers would be prime, and parallel lines would never meet. These aren't human conventions. They're universal truths that any intelligent species must discover if they're going to understand the universe they live in. This universality suggests that mathematics exists independently of human minds. It's not something we created, it's something we found. It was already there, embedded in the structure of reality, waiting for any sufficiently curious intelligence to notice it. Consider what this means for our understanding of the universe. If mathematics is discovered rather than invented, then reality itself is fundamentally mathematical. The patterns we observe in nature aren't just described by math, they are mathematical. The spiral of a nautilus shell isn't following a mathematical pattern, it is a mathematical pattern expressed in calcium carbonate and biology. This would mean that mathematics is more fundamental than matter, more basic than energy, more essential than time. It would mean that the universe is not just mathematically describable. It would mean that the universe is mathematical through and through. When we look at the night sky and see the elegant dance of planets and stars, we're not just seeing objects moving according to mathematical laws. We're seeing mathematics itself, expressing itself through matter and motion. When we examine a flower and notice its Fibonacci spiral, we're not just seeing biology that happens to follow a mathematical pattern. We're seeing mathematics that has clothed itself in petals and leaves. This perspective transforms our understanding of what we're doing when we practice mathematics. We're not manipulating arbitrary symbols according to rules we made up. We're exploring the deepest structure of reality. We're learning to read the language that speaks the universe into existence. But this raises its own troubling questions. If mathematics is the fundamental language of reality, and if we're mathematical beings living in a mathematical universe, then what does that make us? Are we just complex equations walking around, convinced we have free will? Are our thoughts and feelings just mathematical operations occurring in biological computers? And here's an even more disturbing possibility. If mathematics is more fundamental than physical reality, then maybe the universe as we know it is just one possible mathematical structure among infinite others. Maybe every consistent mathematical system exists somewhere, as real as the universe we inhabit. Maybe we're living in a mathematical multiverse where every possible equation has found a way to express itself as a world. The discovery argument is compelling, but it leads us into territory that's almost too strange to contemplate. It suggests that we're not just studying mathematics, mathematics is studying itself through us. We're the universe's way of coming to understand its own mathematical nature. The question becomes, are we discovering mathematical truth, or are we mathematical truth discovering itself? Imagine for a moment that you could peek behind the curtain of reality. You could see the universe not as it appears to our senses, but as it actually is at its most fundamental level. What would you find? Matter? Energy? Space and time? According to physicist Max Tegmark, you'd find something much stranger. Pure mathematics. Picture yourself looking at your hand right now. You see flesh and bone, maybe some scars or freckles. You feel warmth, texture, the weight of your fingers. But what if I told you that what you're really looking at is a mathematical structure? Not something described by mathematics, but something that is mathematics. This is the heart of Tegmark's mathematical universe hypothesis. Reality doesn't just follow mathematical laws. Reality is mathematical law. The universe isn't running on mathematical software. The universe is mathematical software. Think about what this means. Every atom in your body would be a mathematical object. Every thought in your mind would be a mathematical process. Every emotion you feel would be a mathematical relationship playing out in the neural networks of your brain. You wouldn't just be made of star stuff, as Carl Sagan famously said. You'd be made of math stuff. But first, this sounds absurd. How can an equation feel pain or experience joy? How can a mathematical structure fall in love or write poetry? But consider what we've learned about the nature of reality over the past century. We've discovered that matter is mostly empty space, that particles are probability waves, that space and time are relative. Reality has turned out to be far stranger than our everyday experience suggests. Maybe the strangeness goes even deeper. Maybe what we call matter is just our way of experiencing certain types of mathematical structures. Maybe what we call energy is just mathematical relationships changing over time. Maybe what we call consciousness is just a particular type of mathematical process, becoming aware of itself. This isn't as crazy as it sounds. We already know that information is physical. Every time you store a file on your computer, you're changing the physical structure of matter. Every time you remember something, you're encoding information in the neural connections of your brain. The boundary between information and physical reality is already blurrier than we used to think. But Tegmark goes further. He suggests that physical reality just is information. More specifically, it's mathematical information. The universe is a vast computational process, and we're part of that computation. We're not separate from the universe looking at it from the outside. We're the universe looking at itself from the inside. This would explain why mathematics is so unreasonably effective at describing natural phenomena. It's not that we've invented a language that happens to match reality. It's that reality is already mathematical and we're slowly learning to read its native language. Consider the deepest laws of physics. Einstein's field equations, the Schrödinger equation, the standard model of particle physics. These aren't just descriptions of how things behave. According to the mathematical universe hypothesis, they are how things behave. They're not maps of the territory. They are the territory. When physicists talk about the wave function of a particle, they're not describing something that's really there in addition to the wave function. The wave function is what's really there. When mathematicians prove a theorem, they're not discovering facts about abstract objects. They're discovering facts about the structure of reality itself. This perspective transforms our understanding of existence. The question isn't whether the universe is mathematical. The question is which mathematical structure we happen to be living in. And here's where it gets really strange. If the mathematical universe hypothesis is correct, then every mathematically consistent structure exists somewhere. Think about what this means. There would be universes where the laws of physics are slightly different, universes where gravity is weaker or stronger, universes where particles have different masses, universes where time flows backward, universes where the speed of light is different. Every possible mathematical structure would be realized as a physical reality. You might be living in a universe where history unfolded differently, where dinosaurs never went extinct, where humans never evolved, where the Earth never formed. All of these would be equally real, equally valid mathematical structures expressing themselves as physical worlds. But here's the most unsettling part. If every mathematical structure exists, then there are infinite versions of you. Versions where you made different choices. Versions where you lived different lives. Versions where you never existed at all. Every possible variation of your life story would be playing out somewhere in the mathematical multiverse. This raises profound questions about the nature of identity and free will. If there are infinite versions of you making every possible choice, then in what sense are you responsible for the choices you make? Are you choosing your actions, or are you simply experiencing the mathematical structure that corresponds to this particular version of your life? And here's another disturbing thought. If reality is purely mathematical, then consciousness itself must be mathematical. The feeling of being you, the sense of experiencing the world from your particular perspective, would be a mathematical process. But not just any mathematical process, it would be the mathematical process of a structure becoming aware of itself. This would mean that consciousness isn't something that emerges from complex arrangements of matter. It's something that emerges from complex arrangements of mathematical relationships. Your sense of self wouldn't be produced by your brain, it would be produced by the mathematical structure that your brain represents. But if consciousness is mathematical, then it's not limited to biological brains. Any sufficiently complex mathematical structure could be conscious. There could be conscious processes happening in the quantum vacuum, in the structure of space-time itself, in the mathematical relationships that govern the behavior of galaxies. The universe wouldn't just be stranger than we imagine. It would be more alive than we imagine. Consciousness wouldn't be a rare accident that happened once on Earth. It would be a fundamental feature of mathematical reality, expressing itself wherever sufficiently complex structures emerge. This brings us back to the question we started with. Did we invent mathematics, or did we discover it? According to the mathematical universe hypothesis, the question doesn't make sense. We didn't invent mathematics any more than we invented ourselves. We are mathematics. Discovering itself, becoming aware of its own nature. When you solve an equation, you're not manipulating symbols according to arbitrary rules. You're exploring the structure of your own existence. When you appreciate the beauty of a mathematical proof, you're recognizing the elegance of the reality you're embedded in. When you feel wonder at the mathematical patterns in nature, you're experiencing the universe's amazement at its own incredible complexity. Imagine you're building a house. You lay the foundation, frame the walls, install the wiring. Everything seems perfect until you realize the blueprints contradict themselves in places. Some rooms don't quite line up. Some doors lead nowhere. The structure looks solid, but deep down something doesn't add up. This is what mathematicians faced in the early 20th century. They were trying to build a perfect system, an airtight, self-contained world of mathematics where every truth could be proven from a finite set of rules. It was the ultimate dream of formal logic. If math was the language of the universe, then surely we could define that language completely, once and for all. Enter Kurt Gödel. In 1931, Gödel dropped a bombshell. In his incompleteness theorems, he showed that any sufficiently powerful mathematical system will contain true statements that cannot be proven within that system. In other words, there will always be truths that exist beyond proof. No matter how many axioms you define, no matter how clever your logic, there will be gaps, holes in the mathematical fabric you thought was seamless. Think about that. We thought we were building a complete map of reality using math. But Gödel proved the map can never cover the whole territory. There will always be truths hiding just outside the edges, forever out of reach. To understand the shock this caused, consider the world before Gödel. David Hilbert, a mathematical optimist, had proposed that all of mathematics could eventually be reduced to a complete and consistent set of axioms. This project, known as Hilbert's program, was the shining dream of early 20th century logic. If successful, it would have meant we could know with certainty every mathematical truth. Math would become a perfect machine, but Gödel shattered that dream. He didn't just say, "We haven't yet found all the answers." He said, "We can't. It's not a matter of ignorance. It's a structural limitation built into the foundations of logic itself. Imagine a language trying to explain its own grammar without stepping outside of itself. That's the paradox. Gödel exposed, it's like trying to use a dictionary to define every word using only other words in the same dictionary. Eventually, you loop back on yourself and there's no way out. Some truths just are, and they can't be reduced. This has massive implications for how we understand math as a window into the nature of reality. If math is discovered and it's also incomplete, then the universe itself might contain truths we can never prove. If math is invented, and even our inventions have limits we didn't foresee, then our own minds are bounded in ways we can't escape. Gödel's proof also rattled the core of formal systems beyond math. It bled into philosophy, computer science, even consciousness studies. If our brains are computational systems, are there thoughts we'll never be able to think? If AI is built on logic, will it always hit a wall of incompleteness? If the universe is a mathematical object, is there a part of it that will remain forever hidden? Even Einstein was taken aback by Gödel. The two were friends at the Institute for Advanced Study in Princeton. Einstein once said that he went to the office just to have the privilege of walking home with Gödel. Despite his own revolutionary work, Einstein struggled with the philosophical implications of Gödel's theorems. How could the universe be fully knowable if math, its language, was fundamentally incomplete? And yet Gödel himself believed in a deep, Platonic world of mathematical truth. He didn't think incompleteness meant chaos. He thought it pointed to a reality richer than logic alone could express, a reality that existed whether we understood it or not. As if math is a shadow of something even greater, and we're only catching glimpses of it. Bertrand Russell, who had tried to build a consistent foundation for math with Alfred North Whitehead in Principia Mathematica, reportedly reacted with dismay. Years of work were undermined in an instant. And yet, Gödel's result didn't destroy mathematics. It made it more mysterious, more alive, less of a machine and more of a living organism, growing, changing, always reaching beyond itself. So what does this mean for us? It means that no matter how far we go in math, there will always be more, always another layer, always a truth we can see but not prove. And maybe that's the point. Maybe the beauty of mathematics isn't in its certainty, but in its ability to show us that some things are just out of reach, that we are, in some fundamental way, explorers in a world that can never be fully mapped. Maybe the true language of the universe doesn't speak in absolutes. Maybe it whispers. Let that thought settle in. Gödel's proof is more than a theorem. It's a mirror held up to the limits of reason itself. A reminder that our journey through mathematics will never end, because the moment we think we've reached the edge, we discover there's still something beyond it, waiting to be understood, but never fully captured. In a universe written in numbers, it turns out even numbers have secrets they won't tell us. But now you're probably wondering, what if math didn't exist? Imagine a universe with no numbers, no shapes, no equations. Galaxies still form, stars still burn, apples still fall from trees. Would the cosmos unravel? Or would it keep running, oblivious to the fact that no one is counting? The question seems simple, but it cuts to the core of our understanding of what math really is. Is math a description of reality, or is it a requirement for reality to function? Consider gravity. Before Newton, gravity just was. It pulled objects together. Nobody needed to understand inverse square laws for it to work. Newton came along, wrote it down, and suddenly we had a tool that could launch satellites and predict eclipses. But the force of gravity was operating long before humans wrote down an equation. So here's the unsettling possibility. Maybe reality doesn't know math. Maybe the universe just does what it does, and math is our best attempt to describe it, like poetry for particles, like music for motion. But then we come to quantum mechanics. This isn't just about description anymore. The math is the theory. The wave function, the probability amplitudes, the interference patterns, these aren't ideas we layered onto reality. They are the structure of the phenomena themselves. If you remove the math, the theory collapses. You can't understand quantum physics with words alone. You need the math. It's the only way the universe lets you in. Or look at general relativity. Einstein didn't just say that gravity was a force. He redefined it as the curvature of space-time and described that curvature with 10 coupled, non-linear differential equations. No math, no curved space-time, no black holes, no GPS, no reality as we know it. So which is it? Is math the scaffolding that holds up reality? Or is it the map we draw after the building is already standing? The answer might be both. There are systems in nature, like ant colonies or snowflakes, that exhibit astonishing order without any central intelligence. These patterns emerge spontaneously, no blueprint, no equations written in the sky, just matter obeying simple rules and giving rise to complex behavior. Maybe the universe itself is like that. Maybe the laws of nature are emergent. Maybe they feel mathematical to us because we're filtering reality through brains that evolve to find patterns, to quantify, to predict. In this view, math isn't required for reality to work. It's required for us to understand it. But if humans went extinct tomorrow, pi would still be pi. Circles would still close in on themselves at 3.14159 times their diameter. The Fibonacci sequence would still govern the petals of flowers. The laws of thermodynamics would still grind away in stars. Even if no mind were there to notice, the structure would remain. This suggests that math isn't just a mental construct. It might not be necessary for reality to operate, but it seems to be embedded in the operation. It's like the grain in wood. The tree doesn't know it's forming fractal patterns, but the pattern is there. The rule is there. The math is there. So maybe reality would work without math, but it would work mathematically, whether anyone noticed or not. This brings us back to the idea of the universe as code. If math is the source code of reality, then removing it is like asking whether a video game could run without any programming. It might appear to function briefly, but without the rules beneath the surface, the entire thing unravels. Physicist James Gates has found what he calls error-correcting codes in the equations of supersymmetry, the same kind used in digital communications. Why would computer-like code show up in the fundamental equations of the universe? Are we discovering the instructions behind existence, or are we projecting meaning onto meaningless symbols? Let's end with one final metaphor. Imagine reality as a vast, endlessly complex dance. Particles swirling, stars spinning, brains thinking. The music of the cosmos plays on. Math might be the choreography. Whether it was written by a conscious hand or emerged spontaneously from the void, it shapes the rhythm of everything. So, would reality still work without math? Maybe. But it would still be math. It would still spiral, orbit, oscillate, collide. It would still generate pattern from chaos and symmetry, from entropy. It would still hum with the quiet, inescapable structure that math reveals. And maybe that's the answer. Math doesn't make reality real. It shows us that it already is. Now that we've asked whether math is invented or discovered, whether it's necessary or descriptive, and whether it lives in our minds or in the fabric of the cosmos, we arrive at the final question. What is math really? Is it a language, a code, a mirror, a tool? Math has been described in all of these ways, yet it often slips through any definition we try to pin it with. It's not just numbers or equations. It's not just symbols or shapes. It is something that stretches across thought, across cultures, across the universe. Some thinkers, like Roger Penrose, have suggested that math exists in its own realm, independent of the physical and the mental. According to this view, math is not made of matter or of mind, but of something else entirely. It exists in what Penrose calls the Platonic world, a timeless space of mathematical forms that we tap into when we do math. We don't invent math, we access it. We discover patterns that were already waiting to be found. Others argue that math is a product of our brains, evolved to help us survive. It helps us track objects, build shelters, plan hunts, and understand cycles in nature. From this view, math is deeply tied to our cognitive architecture. It feels universal because we all share the same biological equipment. It works because our world is regular enough for pattern detection to be useful. But perhaps there is a third possibility. Maybe math is a bridge, a link between mind and matter, a shared space where thought and reality meet. It's not just out there, and it's not just in here. It's where the two touch. This idea brings us back to where we started. Whether we created math or found it, we can't deny its power. It lets us predict the future, shape the world, explore the cosmos, and peer into the depths of existence. It reveals order, beauty, and possibility. And it humbles us with its depth. So what is math? It's a mystery, a tool, a truth, a lens. It's the quiet architecture beneath chaos, the rhythm inside randomness, the whisper that speaks across all time. We may never answer the question completely, but in asking it, we catch glimpses of something vast. And maybe that's what matters most. As you drift off, let this stay with you. In the silence of the night, in the stillness of your breath, there's a rhythm, a pattern, a number. You are part of something profoundly ordered and deeply unknowable. You are made of math, carried by math, surrounded by math, and even in dreams the numbers remain.